So this one is about lattice paths, and it says starting at the top left corner of a 2 by 2 grid, and only being able to move right and down, there are exactly 6 routes to the bottom right corner. And the question is quite simple. It's do the same thing but for a 20 by 20 grid. And I think the way to solve this one, or the way I solved it when I did it about 2 years ago, was actually just to think about the pattern, write down some simple cases, spot the pattern, and then use the computer for the last bit. So we can do much of the logic without using a computer. So let's go ahead and do that. So here's a very well drawn grid that I've made earlier, and what we're going to be considering is the number of ways that there are starting at this point here to get to all of the other points in the grid. So it starts off pretty easy, and I think there's a special laser on this Jamboard thing, isn't there? So if we want to go, oh yeah. So if we want to go to this point, there's clearly one way to do it. You just go along that edge, and indeed that's going to be the same for all of the points along the top row, right? There's only one way to get to this point if we're only allowed to go right and down, and that way is just to go straight there across the top. So if I start adding in little numbers, and I'll put them in blue or something just to make them a bit different. Maybe I should actually use text, but whatever. And this is going to take forever, isn't it? But these are all ones across the top. So this isn't that interesting, but it's it's important for later. And likewise, by the same logic, going along the bottom, they're all going to be ones, or going along the left hand side, I guess. And the interesting question is to get to that's a circle, not a laser. To get to this point here, how many ways are doing it? And it's like, well, you can go this way, or you can go this way. So there's clearly 2 ways of getting there. And I think the other way to think about that is, well, I can get here by adding up. I can get here from this point, or from this point, and from this point. Therefore, to get to this point, I just need to add the number of ways from here to the number of ways from here to get my answer. So if I want to think about getting to this point, I know that there are 2 ways to get here, so I can go like that to get to that point, or I can go from here like that. So the total becomes 3. And then likewise here, it's 4, because there are 3 ways to get to this point, and 1 way to get to this point. Likewise here, it's 5. And then indeed we can do the same thing going along here, so 3 by symmetry, I guess, as mathematicians often like to say. And then indeed we reproduce the answer that's given in the initial sort of problem, which is that there are 6 ways to get to the end here. Great. And this, if you've done sort of maths at university, or maybe even at school, you'll probably recognise this pattern already. This 1 4 6 4 1 stuff, and then this is clearly a 10 here because 6 ways from there, 4 ways from there, adds them up, you get 10. Likewise here, we could keep going with this, but I think we've spotted the pattern, and it's perhaps easiest to spot if I sort of if I take a screenshot of this and rotate it. We might see something familiar, so I'll just copy that. If it decides to load, is it going to load? Who knows? I think you could probably spot it anyway, but this looks a hell of a lot like Pascal's triangle. And yeah, so I basically just spotted that this is Pascal's triangle, is what these results are, and there is a way to compute the elements of Pascal's triangle, which is this n-choose k stuff, and somewhere I hope it's going to tell us what the formula for a binomial coefficient is, if you don't already know, but it looks like it's not telling. Okay, so this is the formula for a binomial coefficient that we're going to use, and we just need to know what values of n and k to choose. And the other thing that I found interesting when I was looking at this article was there was a picture of like Pascal's triangle as drawn by Pascal himself, and so got it here as well, and it looks like incredibly similar to what we've been doing. In fact, it's basically the same as this, except he has slightly nicer handwriting than me. Okay, so in the sort of n by n case, clearly the sort of top of the binomial coefficient has to be 2n, because there are 2n total things that we're looking at, and the bottom of the binomial coefficient is going to be n. Therefore, the answer is 2n choose n, or written down, I guess, in pseudocode, it's like 2n factorial over n factorial multiplied by n factorial. And just to be super clear, these guys are get a set of brackets like that. So we just need to compute this a factorial function, really. And I suppose there's some sort of cancellation you could do here, but you know, let's just try it with a naive approach and literally just compute this. And to compute factorials, there's this quite fun Haskell that I'll link, which is about the many different ways to compute factorials in Haskell. And you know, it starts off fairly normal, and then it starts going a bit crazy. And they start using type level stuff, and they start using, you know, the Y combinator and all sorts of mysterious things like that that I don't understand. However, I think the simplest way to compute a factorial is the tenured professor variant, which is way at the bottom somewhere, which is it's just a product, right? So we can do that. And I guess technically this isn't correct because 0 factorial is 1, but, you know, whatever. So let's do that. So we just need a function called factorial, which takes an... Can we get away with integers? Probably. 20... Well, it's 20 factorial, but if I multiply... No, let's do big ints, just to be safe. I'm a coward, clearly. And we'll do sort of... You know, we don't have Haskell's, like, lazy list thing, but we'll just do our classic iterator.range, and we'll go from 1. So, you know, my factorial is also technically not really a factorial, but whatever. We'll go to... Oh no, we just want an int. We want to return a big int, right? No, we'll map them to big ints in here. Okay. So n plus 1, and we'll do the sort of map it to a big int, just in case. Possibly won't need it, but I like to play it safe. And then we'll take the products like that. So let's just check that this really does give us the right answer. So we know that 3 factorial should be 6, right? Yes, good. And that took 0.040 seconds, great. And then we can literally just write this down as, let's maybe just say n is 20 here. Then we can maybe just write down the answer in terms of n. So 2n, not 8, not 28n, that'd be pretty big, over factorial of n times by factorial of n, like that. So that should give us the answer. Let's see. That's a big number, right? I don't know if that's a big int though, but I think when I'm doing this factorial of 2n, like that is, it still only took 0.040 seconds. So like as I was writing this, I was thinking of optimizations, but to be honest, we're not going to need them. Yagni, you ain't going to need it. That's a good software principle, I think. And that is the correct answer, so that's great. And I think the other thing to think about is, like, usually when you have this sort of binomial coefficient, this is telling us the number of ways to choose n items from 2n items. So maybe there's some sort of interpretation that we can link back to the original problem. However, my interpretation in my head is maybe a bit different, and it might be wrong. I'm not very good at this sort of thing, but like if we have our sort of n by n grids, to my mind, we want to choose arrangements of 2n objects, and the way to see that is sort of 2n factorial. That's the possible orderings of those. However, for the ones that are going to the right, we don't care about, there's a sort of degeneracy in how those are ordered, so we can divide by n factorial. Furthermore, for the ones that are going down, there's another degeneracy, so we can divide by n factorial again. And that's all very hand-wavy, and, like, isn't how I approached the problem. The way I approached it was literally just to write down this I guess, path enumeration, spot the pattern, and then notice that it's Pascal's triangle, and then turn that back into code at the end, which I think is a perfectly legitimate way of solving these problems. Anyway, yeah, I'm pretty happy with the answer. And yeah, I think this is the first video I've done in a sort of single take, actually. So yeah, thank you for watching, and see you next time. Yeah, so I think I might have spoken a bit too soon about the single take thing. There's a correction I want to make, which is I said that their definition of factorial in Haskell was wrong, but it's not. It's correct. So they defined it as this, I believe. So 1 dot 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 n, and that's the definition. And I said that, well, that's not correct for 0 because it's gonna throw an error, but it doesn't. It works perfectly. So what's going on here is that if I do 1 dot dot 0 in Haskell, that's going to give me an empty list, and then if I take the products of an empty list, that's going to give me 1. And I didn't know that. But it makes sense, because the way that you would usually define a product is with a sort of fold left, and you usually give it a neutral element, like which for product is 1, because you're usually going to use a monoid for multiplication, and I suspect that's probably how this works under the hood, but I don't, I'm not going to go into it because I don't fully understand it. I guess the other thing that's kind of interesting is what does my one do if I give it a 0 as an input, and I think I'm betting that Scala probably also has a neutral element for products, or it might throw an error. I'm not actually sure. So yeah, so I bet if we look at the implementation, it's probably going to be like, yeah, so if it's empty, then just give us 1, otherwise reduce it. Well, that makes sense, right? So that's pretty cool. So it actually means like these are safe functions to use, because in Scala, if you try and sort of use reduce on an empty list, for example, that usually just goes completely wrong. That usually just goes haywire. So if I was to do that, I think that's going to throw an error, right? Well, I mean, you have to be in the Scala sort of REPL, obviously. But, so if I do that, I think that's going to be like, there's no elements. Exactly. Oh, well, okay. So if it was a sort of, fine. If I did list.empty of ints or something, I think that's going to throw an error. Yeah. So because it's not safe to use reduce on an empty list. So yeah. So I've learned something today. Anyway, I did kind of jinx it when I was like, this is the first one I've done in a single take. So yeah, but important to check that you're right when you say stuff, and learn from your mistakes. Alright, see you later again, and thank you for watching again. Bye.